Now let's look at series that have the variable x in them. We've spent a lot of time talking about series with just, a fixed value. We have a formula for our summands, and we want to know whether or not that formula actually converges to a real number. If the series is convergent, then we can actually find a value for that series. If it's divergent, that means that, even though we can write this formula, it's not really a coherent number that we can manipulate, right? Sometimes we just write a formula and it's nonsensical, like 1 divided by 0. Well, what we're going to do is we'd like to use series to describe functions, right? A function is just some formula with a variable in it. Different values of the variable will give us different outputs for the function. And part of working with functions is knowing when that formula is valid. For example, the square root function, square root of x, is only valid as long as x is a number greater than or equal to 0. It's just incoherent if I put a negative value of x in there. So what I'd like to practice is using the series convergence tests to know when a series converges based on the value of x that I have. So here, I've got the sum n from 0 to infinity of x to the power n. Now this is a geometric series. Just I use the letter x instead of the letter r. But I can use the geometric series test very quickly here. This converges as long as x is a number whose absolute value is less than 1. If x's absolute value is greater than or equal to 1, then the series diverges. So this means that the geometric series gives me a function of x, but the domain of that function is only for values of x that are close to the number 0. Right? My absolute value is measuring distance from the number 0, and that distance has to be strictly less than 1. Let's make this a little bit more complicated. How about instead of x to the power n, I've got x to the power 2n. Okay. Well, this is not terribly far removed from the geometric series. What I'll do is I will group this. X to the power 2n is the same thing as squaring the number x and then raising it to the nth power. So here, this will be convergent when the absolute value of x squared is less than 1. Well, squaring that x, that's going to be the same as just having absolute value of x less than 1. And similarly, it'll be divergent when x squared has absolute value greater than or equal to 1. But again, I can simplify this. The only way that x squared can have absolute value greater than or equal to 1 is that x itself has absolute value greater than or equal to 1. Squaring a number whose absolute value is less than 1 makes it smaller. Squaring a number whose absolute value is greater than 1 makes it bigger. Squaring a number whose absolute value is equal to 1 your absolute value will still be equal to 1. All right, well, what else can I do to this series? Well, maybe I don't have x to some power. I could have some other expression, maybe a polynomial expression. So the next problem that I assigned was looking at this series x minus 3 to the power n. Well, even though the stuff inside the parentheses is more complicated now, this is still a geometric series, and I'm still going to use the geometric series test to determine what the domain of this function is. What values of x make the series converge? So I can say by the geometric series test, this converges when, well, the absolute value of my r, my common ratio, needs to be strictly less than 1. So here is my r to the power n. Okay. Well, what I'm going to do is I've got this absolute value. And I can think of this as describing a domain on the number line. So what's the largest that x could be? What's the smallest that x can be? Well, what I'll do is I'll say that for this inequality, the quantity x minus 3 could be positive or it could be negative. I lose that information when I take the absolute value. So to try to recover that information, I'll say that x minus 3 definitely has to be less than 1. But just in case it's negative, it also has to be greater than negative 1. Numbers that are less than negative 1 have their absolute value greater than positive 1, right? Absolute value of minus 5 is positive 5. And I don't want that to happen accidentally. Okay, well, with this inequality, I'm going to add 3 to everything that shows up. So x has to be a number between positive 2 and positive 4. A different way I could think about this is that in between 2 and 4, exactly in between, is the number 3. And I'm allowed to go 1 unit away in either direction. If I go exactly 1 unit away, that's too far. The series will diverge. But as long as I am less than 1 unit away, I'm good. And I can see that information spelled out here in the inequality. This absolute value of the difference, this is measuring the distance from x to the number 3. That distance has to be strictly less than 1. So I can go from this inequality to more geometric reasoning in terms of a center location, number 3, and a maximum distance. Distance has to be less than 1. All right. So those examples are showing me how I can use geometric series when there is a variable x involved. Not every series that I look at is going to be a geometric series. So maybe I have something like x to the power n divided by 2 to the power n plus 1. That's not a geometric series because I cannot write this as some formula all raised to the power n. I'm raising 2 to the power n, and then I'm adding 1. So I will need to use a different test for convergence here. For the same reason that this is not a geometric series, I won't be able to use the ratio test, at least not very efficiently. I could try it, but at some point I'll have to take the nth root of the quantity 2n plus 1, 2 to the n plus 1, and that's going to get a little hairy. It's possible, but for this problem, I think I would prefer to use the ratio test. So I'll take the limit as n goes to positive infinity. I have my absolute value of the formula evaluated at n plus 1. So numerator, x to the power n plus 1, denominator, 2 to the power n plus 1, and then I add 1 to that power. I add 1 to that quantity. Then I have to divide by the same formula evaluated at n. Here, I'm going to achieve that by multiplying by its reciprocal. Whenever I divide by a fraction, I achieve the same result by multiplying by that fraction but upside down, and I get this formula. Well, for this example, the absolute value bars are redundant. They are important for the ratio test in general, but this 2 to the power n plus 1, that's always going to be positive, so that's not giving me any trouble. Oh, that x is a variable, even though I've just written it as x. Do remember, there is the possibility that x represents a negative number. Even though I don't have a minus sign written in this formula, I need to account for the possibility that x is already representing a negative number. Now, when I go to clean up this formula, there's one more power of x on the numerator than there is on the denominator. So I'll have the absolute value of x on my numerator. Then I'll have this fraction involving powers of 2. And here is where the absolute values are actually redundant. Powers of 2 are going to be positive, and I'm dividing by them. That's still positive, so we're good. And what I'm going to do is I'll try to grab the whole thing. I'll try to factor. So in the limit, I've got n going to infinity. I've got this absolute value of x, and there's one more power of 2 on the denominator than there is on the numerator. So maybe I can try pulling that out. If I do pull that out, what do I have left over? Numerator hasn't changed. That's 2 to the power n, all plus 1. Well, the denominator is 2 to the power n plus 1 divided by n. Okay. 1 divided by 2, excuse me. So in the limit, this numerator and this denominator are both going to positive infinity. Now, there's a couple ways you can handle this. You might want to multiply the numerator and denominator both by 1 over 2 to the power n. Because I'm doing the same operation to the numerator and the denominator, I can shuffle the formula around without changing the value that that formula produces. You could also use L'Hopital's rule here, replace that numerator and replace the denominator both by their derivatives, which will be log of 2 times 2 to the n. Either way, this limit produces the absolute value of x divided by 2. Right. Now, the ratio test says that whatever I get for the limit, as long as the number is less than 1, the series converges. Well, to make the absolute value of x divided by 2 less than 1, that would mean that x itself has to be between positive 2 and negative 2. Cool. And then my test will say the series converges. Well, where do I get divergence using the ratio test? I'll say the series diverges as long as x is a number where this fraction is bigger than 1. Okay, well then that would mean that either x is a number strictly bigger than 2, or x is a number strictly less than -2. So there's going to be 2 different regions where this series diverges. But notice that there's also the inconclusive result. If I'm going to use the ratio test or the root test for this kind of work, I have to say that the test is inconclusive for x equals 2 and for x equals -2. Both of these values of x, when I put them into my formula, I get a limit of exactly 1. And that is where the ratio test does not produce an answer. Maybe the series converges for that value of x. Maybe the series diverges for that value of x, but I just do not have enough information to figure that out using this test. It's important to be aware of the blind spots that I can have for these examples. Moving on. The next problem I assigned was a sum from n equals 0 to infinity, x to the power n squared plus n, all divided by 2. So I'm taking powers of x according to this formula. Well, this time around, because I just have that number x raised to a power, I want to see if the ratio test can help me. So in the ratio test, I would be looking at absolute value x to the power n plus 1 squared plus n plus 1. That exponent is divided by 2. And then the denominator is going to be x to the power n squared plus n, all divided by 2. And I want the limit of all this as n goes to positive infinity. Well, this isn't impossible. I can definitely work with this. But simplifying that exponent is going to be a little tricky. Let me try the root test instead, just to see if that looks any nicer. So taking the nth root of the formula with absolute values. Well, I still need to be careful with this, but already I've got less of a formula I have to worry about. And when I go to combine these exponents, and it's actually going to be not too bad. So I'll have the absolute value of x, and when I combine exponents in this way, raise x to a power and then raise it to another power, what I have left is the product of those powers. So my numerator is n squared plus n in the exponent. My denominator is 2n. Oh, well, that's actually going to cancel. If I have numerator n squared plus n and I divide by 2n, well, what I will have left over is numerator n plus 1, denominator 2. Now here's where I need to be careful. I am looking at a limit where I take x to a power. And that power is growing. As n goes to infinity, that exponent is going to go to infinity. The behavior of this is going to depend on that number, x. So let me think about this. This is the limit I care about. Well, what happens with this absolute value? I know that this absolute value is going to be 0 or greater. And when I raise it to these large powers, the behavior that I see is going to be different depending on if the absolute value is less than 1, whether the absolute value is equal to 1, or whether the absolute value is greater than 1. For numbers less than 1, when I take very large powers, and these numbers are also greater than 0, then in the limit, I'll get 0, right? 0 to any power is just itself. Or if I have some positive number that's less than 1, like 3/4, as I take higher and higher powers of that number, I'll be getting closer and closer to 0. If this absolute value was exactly equal to 1, well, 1 to any power is itself, and I just get 1. And then if my absolute value is greater than 1, taking large powers of a number greater than 1 will tend towards positive infinity. Okay. So that's the result of my limit. I get 3 different values depending on what x I put in. Now I need to translate this into the outcome of the ratio test. So if x is a number between 0 and 1, well, the absolute value of x, excuse me, the series converges. My limit exists, it's the number 0. The ratio test says that my series will converge for that value of x. If x has absolute value greater than 1, the series diverges. Whether that x is a positive number or a negative number. But the very last outcome here, if x is exactly plus or minus 1, I take the absolute value of that thing, I take higher and higher powers. The limit is exactly 1. The test is inconclusive. So once again, I need to be aware of the blind spot for using the root test and for the ratio test as well. Here, I can say that the series definitely converges. Well, for absolute values, that would mean that x is a number strictly between -1 and +1. It'll definitely diverge if x is a number greater than 1, or if x is a number less than -1. I've got these 2 spots right on the boundary, right where the behavior changes from convergent to divergent, where I'll need to use another test. Maybe I'll want to use the alternating series test if x equals -1. Maybe I'll want to use a comparison test if x equals +1, or maybe the basic divergence test, but something different from the root test. The root test is not going to be able to give me information for its 2 blind spots there. Okay, I think that's enough for this video.